between different continents. So what I'm going to present to you today will be from work done indeed in different continents, but it will be continuation of a research line that is rooted right at the intersection of interval timing and decision making. So we'll be exploring that very border between interval timing research and decision making research. I assume you can see my slides. I will particularly talk about the recent discovery that we did with Balci a few years ago, and decades-long, not decades-long, well, maybe decade-long research that has set the path to that discovery. This is the conceptual map that I'll try to cover today. I might end up dropping certain boxes from this conceptual map depending on the time, but I will be mainly talking about the interaction between interval timing and decision making, with a particular focus on the role of timing uncertainty in determining reward rate maximizing decisions or choices. So I'll be covering this both in relation to temporal decision making, something that most of us study. When I look at the participant list, I can see that most of you guys will be familiar with the terms that I'm going to use, the procedures. But I will also talk about the role of timing uncertainty in determining reward rate maximizing decisions in perceptual decision making, and that will not be necessarily familiar to all of you. If I find time, I suspect that I might not, I'll talk about the overlap between decision making and interval timing at the level of generative processes. I know that Pat Simon talked about our model of interval timing, time adaptive opponent Poisson diffusion model of timing. So maybe I'll just capitalize on the fact that he did cover that already. At the end of my talk, I would like to talk about this discovery that I have just mentioned, what I call metric error monitoring today. Okay. Just to make sure that I cover all the bases, even for those participants who are not familiar with interval timing, we define interval timing as the ability to perceive, to remember, and organize behaviors around periods that range from seconds to minutes. Okay, so that is the time scale that we will be working on, that we'll be talking about today. And as most of you know, one of the prominent psychophysical properties of interval timing is its scalar property. Basically, the fact that the standard deviation of time responses, the ratio of the standard deviation of time responses to the mean of those time responses is constant. So that basically refers to the constancy of the coefficient of variation. Okay. Why am I mentioning this? Not because it's a prominent property. It is kind of like it's a property that you would have to explain if you are developing a model of interval timing, for instance. I'm mentioning it particularly because I'll be using this property throughout my talk. Okay, and it's one of the ways to explain Weber's law in the domain of interval timing, namely the fact that the discriminability of T intervals is a function of their ratios rather than the absolute difference between them. So one of the predictions of scalar property is the fact that when you express time responses on a relative time scale. So what do I mean by relative time scale? If you take the absolute time scale and divide it by the target time, you are relativizing time. So the prediction is on a relative time scale, time responses should superimpose. So on the left, so these data come from the peak procedure from three different organisms: rats, humans, and mice. This is a task in which participants are asked or are trained to receive reinforcement reward after a fixed amount of time. So the first response after a fixed amount of time results in the reinforcement of the response, which is what we call the fixed interval schedule. Then we intermix what we call peak trials with the fixed interval trials. And these peak trials basically last much longer than the fixed interval trials, and participants or subjects do not receive any reward. And what we are looking at here is the reward rate as a function of time in the peak interval trials on the left on an absolute time scale. So as you can see, these subjects are tested with different target intervals. And one of the things that will hit your eye is that the response curves for longer target intervals are wider than the response curves for the shorter time intervals. And that is what scalar property suggests. And when you relativize the time, which is what is done on the right panel, what you see is that these response curves invariably superpose, which again confirms the scalar property of interval time. Okay, so it seems like this is a ubiquitous property that we can safely rely on in making assumptions regarding the role of interval timing in decision making. Now, this has been said, there are conditions under which scalar property is violated. Okay, so I'm just telling you about the majority of the cases here, but it doesn't cover all empirical grounds. Okay, so now I'll talk about the role of time without certainty in determining reward rate maximizing time decisions. And to do that, now there are many scenarios that we have used. Some of them very complex, in which there was a hidden reward, exponential reward structure as a function of time, and the participants were basically tested such that they had to maximize their reward under those conditions. We would impose deadlines. In some other cases, participants were asked to make choices between different timed options. This is the simplest of those procedures, which is called the differential reinforcement of low rates of responding. In this procedure, subjects are asked to wait for a minimum amount of time between their responses. So if they have emitted a response, let's say that they emitted a response, they received a reward. To be able to receive the next reward, they would have to wait longer than a minimum interval. So in a DRL 5-second schedule, for instance, to be able to get a reward, animals would have to wait at least 5 seconds between their responses. Okay. So here is just an illustration of that. On top, you see responses. On the bottom, if there's a green circle, that means that response has been reinforced. As you can see, early responses are not reinforced, but if the animal is waiting long enough, response is reinforced. Okay, so that's really easy to run in an operand box. That's just as easy to run on a computer screen. So we have tested mice, rats, and humans in this task. Now, the critical unit of analysis in this task is the entire response time distributions, so entire response times. On the left, you see an example entire response time distribution that we have gathered from rats, and on the right, you see entire response time distributions that we have gathered from humans. This data comes from work that I did with David Freestone. One thing that hits the eye here is that the entire response time distributions have a skew to the right. So in fact, these distributions tend to be inverse Gaussian distributed, which is rather important, but I'll come to that later. And another thing that might hit your eye is that when you look at the rat inter-response time distributions, you have this exponential component here. I don't know if you can see my cursor. So those are trials in which rats are presumably losing temporal control over their responding. Okay, they are being impulsive. Or another alternative is maybe they are exploring the temporal scape to see if the reinforcement occurs earlier once in a while. Okay, so that's something that is to study, actually, an interesting question there. But impulsivity can take a different form here. These inter-response time distributions might be left shifted with respect to the minimum wait time. Okay, so animals might not be waiting long enough. But if you train rats, mice, obviously humans, with short enough DRL schedules, let's say 24-second DRL schedule, and if you give them enough training, what you observe is that the mean of the inter-response times tend to be longer than that minimum wait time, okay? And your first reaction might be, well, this is a misestimation of the time interval that is peculiar to this task, okay? I will argue that this is an adaptive response, as you can imagine. So I'll jump into that right away. Why is this an adaptive response? Well, the DRL schedule poses a very interesting trade-off between the speed and the accuracy of responses, which is kind of analogous to the speed accuracy trade-off in perceptual decision-making, which is something that I will also talk about today. So the trade-off is between the probability of a time response being reinforced and the average time cost of rewards. And the source of this trade-off is timing uncertainty. That is, a subject might be aiming to respond, let's say, at 1.2 seconds, but from one trial to the next, there will be substantial variability in their responses, time responses. So they don't know exactly when their time response will be, but they can aim at the target. The important thing here is that the optimal balance between the probability of a response being reinforced and the time cost of reinforcement depends on the level of this timing uncertainty. Okay. Now remember that the reward rate in this task is probability of getting reinforcement divided by the average cost of that reinforcement. So the subject might aim to respond much later in the trial, in which case the subject might be increasing the probability of getting reinforced, getting the reward. But at the same time, such a strategy would be linearly increasing the time cost of that reward. Okay. So you are decreasing basically the number of opportunities at which you can get reinforcement. A subject might adopt a different strategy, might aim to respond early to reduce the time cost of rewards. But in that case, they would be decreasing the probability of getting reinforcement. Okay, so in order to demonstrate this, I just built these two illustrations. On the top, you see a hypothetical subject with a low timing uncertainty. I believe this was CV of 0.1. And on the bottom, you see a participant with a high timing uncertainty. I believe I implemented CV of 0.2. In each panel, in each figure, we have two panels. Okay, the top panel shows what happens to the distribution of inter-response times as the participant is aiming at different time intervals, wait times. And on the bottom, you will see a corresponding expected reward rate curve for that participant, okay, for different target wait times. Okay, let me play that. As you can see, as the subject is aiming at later time points in the trial, the distribution of inter-response times become wider and wider. So that is the scalar property that we have assumed, right? And on the bottom, as I said, you see the corresponding expected reward rates for different target wait times. And you can see for this participant with a CV of 0.1, the optimal wait time is somewhere around 1.2. Okay. So this is the kind of picture that we are after. Let's see what happens to a participant with a higher timing uncertainty in the same task with the same schedule. Again, this is just an illustration. I assumed inverse Gaussian distributions here. The distributions are getting wider. Corresponding expected reward rate curve at the bottom. You can see that the optimal wait time for this participant with higher timing uncertainty is later than this one. So the only difference between the two is one of them has a low timing uncertainty, the other one has high timing uncertainty. Okay, so basically based on such a computation, you can build a prescription. If you know participants' timing uncertainty level, you can prescribe an optimal wait time. Okay, And that's indeed what I'm going to use to evaluate the empirical performance of participants. So as I said, we have tested rats, mice, humans in this task. The results are more or less similar. I choose to present this data because I find it very interesting in the sense that we treated human participants just like we treat our non-human subjects. We brought them to the room and we said, look, here's a key. You can get reward when you press that key or not. That was the only instruction that they got. Okay, which is essentially what you do with rats, mice, right? You don't even get to say that. So we had two groups of participants here, tested over many sessions. This data was collected by Bilgehan Çavdaroğlu, who recently received his PhD from University of Toronto. We had two groups of participants. The first group of participants had no penalty for responding early. Okay, they would just miss the reward. The second group of participants had penalty for responding early. Okay, so this was a variant of the DRL schedule. Now remember that each response in this task, reinforced or not, resets the elapsed time. So if you keep pressing the key again and again and again, you might not get reinforcement at all. All right. All right. So these are heat maps that show the expected reward rate for different target intervals on the x-axis and different levels of timing uncertainty on the y-axis. Okay. It's not normalized. So obviously participants with a low timing uncertainty would earn a lot more than participants with high timing uncertainty. So this basically gets lower and lower. What you need to look at here is the black curve that marks the ridge of this heat map. Okay, for different levels of timing uncertainty. So that is the prescription. That says if your CV, coefficient of variation, standard deviation over the mean, is 0.35, then you should wait this long to maximize your reward rate. If your CV is somewhere around 0.1, you should wait this long to maximize your reward rate. Each symbol here is the average wait time of an individual participant. I think you can see that those participants are very closely following that prescription, that optimal performance curve. And on the right, I showed in the form of a regression, the relationship between empirical and optimal wait times are near unity. It's very close to the identity line. Okay. We see a very similar picture when participants were penalized for early responses. I mean, notice that the optimal performance curve is right shifted in the second group, right? Because now, if you respond early, you get punishment penalty. So the optimal response curve is right shifted. But even in this case, you do have these participants' responses that very closely follow that prescription. Except for this one, this participant has been following me from United States to Turkey, I feel like. Okay, we always have the one outlier in almost all experiments that we have. Okay, so that seems like an accuracy bias. Actually, that will become very relevant in the second part of my talk. Again, when you exclude that one outlier, you see a near unity relationship between optimal and empirical wait times. And in this task, our participants earned more than 97%, as far as I remember, of the maximum possible expected gain that they could earn in this task. Okay, we see similar things with rats. Sometimes you get a bias, so they do also follow the optimal performance curve, but with a bias. So the curvature is more or less the same, but it's slightly left shifted. With mice, we get similar results. We have tested mice. This data was also collected by Bilgehan from humans to mice. So he had a very interesting graduate work with me. Here we used fixed consecutive number schedule. So this is similar to the DRL schedule that I have just described. But in this case, the mice are pressing, they would get reinforcement after pressing the lever for a minimum number of times instead of a minimum duration. Different from the DRL schedule, subjects in this task produce the minimum number of presses on one lever, and they can claim their reward by pressing the second lever. So if they press the second lever after not completing that minimum number, they don't get reward, and the number of responses that have been accrued resets. But if they do claim their reward after pressing the first lever for a minimum number of times, they get the reward, okay? You can also see the scalar property here, right? So as the target number increases, you see that the response curves become wider and wider. So that's great to see. That's also in the literature, scalar property holding for numerosity representations. And you also see this rightward shift with respect to the minimum number of times they should press the lever to get reward. So that is an adaptive bias, as I mentioned. On the right, you do see average reward rate curves as a function of target number of times to press the lever under different schedules. Those circles are average empirical mean number of responses emitted by participants under different schedules. As you can see that these mice can really find the peak of those expected reward rate curves, meaning that they can really maximize their reward rate, okay? As I said, this was the simplest task. That's why it's well fit for this talk, because you can quickly talk about it. It's easy to explain. But we have seen such a performance in much more complex tasks. We have seen such a performance in mice, in humans. This is actually data that came from work that Pat and I did now 10 years ago now, where participants tried to get as close as possible to a deadline, but not miss it, as the reward that they could earn increased exponentially as a function of time until that deadline. But if they missed that deadline, it became zero. So it's like submitting a grant, right? You have a deadline, you're trying to perfect things. As you make more perfection, of course, you have a better chance of getting funded. But if you miss the deadline, you get $0, right? So it's a task similar to that. This is the prescriptive curve, optimal performance curve. These are participants. You can see that they can closely follow that optimal performance curve. Mice can do this too. So that's work that I did with Ezgi Gür that has been published in Animal Cognition. You can see that data from mice in that paper. Okay, so my interim conclusion is that humans and non-human animals can take normative account of temporal and numerical uncertainty in their temporal and numerical decision-making. This seems to be a ubiquitous feature of temporal and numerical decision-making. And now I'll talk about a similar relationship in the domain of perceptual decision-making, okay? Which is something that has not been studied as much. So now we are connecting those three boxes. In our daily life, we do a lot of simple choices. This could be changing the traffic lane as you're driving. It could be trying to pick the faster cashier at the grocery store, okay? What we do is we are exposed to some sensory evidence. We presumably accumulate that evidence, and we are trying to reach a decision that is accurate and at the same time fast, okay? Because that is the strategy that would maximize your reward rate. In the lab, one of the common procedures that's used to study such simple decisions is the random dot motion discrimination task, okay? This is a two alternative force choice task in which participants are shown a cloud of dots that are moving, and participants' job is to decide if those dots are moving coherently to the left or right. Now, it's not as easy as it sounds because there is noise in the stimulus, okay? So only a subgroup of those dots will be moving coherently to the left or right, whereas the rest will be moving in random directions. So I just want to demonstrate this. I don't know how well that looks on your screen. Try to decide if those dots are moving left or right. I presume this was a very difficult task because there was no signal there. All those dots were moving in random direction. Zero signal to noise ratio. Okay. And it probably, even if you might have reached a decision, but that probably took a long time within that fixed viewing time. Look at this one. Is that easier? That's 30% signal in there. In this task too, the strategy that would maximize your reward rate requires you to find the optimal balance between the speed and accuracy of your decisions. Okay, so you have to decide how much evidence you want to accumulate before making a choice, and that will determine the accuracy and speed of your decision. You can choose to look at such stimulus. Let's say that it was free viewing time. It went on and on until you made a decision. You could choose to observe that stimulus for a very long time to increase the likelihood of the accuracy of your choice. But in that case, you would be losing from your decision time. So you would be decreasing the number of times, number of opportunities in which you could earn a reward. For instance, if each correct choice was indeed reinforced. Or you could adopt a different strategy. You can say, look, I'm not going to watch that stimulus long. I'll make quick judgments so that I increase the number of opportunities to get the reward. But in that case, the likelihood of your choice being accurate will decrease because you'll be relying on less evidence. Okay. All right, I did that. So now I'd like to touch on this issue within a specific decision theoretic framework. So I'll use the drift diffusion model to demonstrate to you the optimal balance between the speed and accuracy of decisions. I'll use the reduced form. This is an extended form of DVM illustrated here, but the assumptions are the same. Most of the assumptions are the same. The primary assumption of the drift diffusion model is that sensory evidence is noisy. The difference between evidence supporting two alternatives is the decision variable. So in our previous example, it would be evidence supporting leftward motion versus rightward motion. That is the decision variable. This variable that's subject to noise is integrated over time, and it's integrated according to this equation where dx basically shows the average change in the location of decision variable within the decision space over a very short time interval dt, and that change is composed of two components: an average drift rate, the average rate at which you are approaching the correct threshold, and the diffusion coefficient, which is basically white noise, Gaussian distributed white noise with a mean of 0 and standard deviation of c, let's say. And you do start from a 0 point. So when that decision variable crosses one of the two thresholds, you make the corresponding choice, and the time that it takes your decision variable to hit one of those thresholds denotes your decision time. Okay. Now, in the reduced form of this model, you don't assume variability in the starting points, in the non-decision times, in the drift rates, and things like that. You can have an extended form in which you can introduce all those parameters, but for the sake of this talk today, we will not assume those variabilities. Okay. So then, how do you modulate your strategy in this in such a framework? As I said, you can choose to be faster, to increase the number of decisions that you make within a fixed amount of time, and you can implement that by bringing those thresholds closer together. Obviously, you would hit one of those thresholds earlier, but the chance of hitting the right threshold will decrease because of this noise in the evidence accumulation process. Or you can do the opposite. You can increase the distance between those two thresholds, which will result in longer decision times because you will have to accumulate more evidence to hit one of those thresholds. But the risk of hitting the wrong threshold due to this diffusion coefficient will decrease. Okay. The question is, Where is that sweet balance between those two? How do you find that optimal threshold? And what does it have anything to do with timing uncertainty that I was mentioning to you already? Okay. Before doing that, I would like to demonstrate to you that this is a very nice and robust theoretical tool to use in decision-making research, even in non-human animals. So this is data that come from children. Here, I'll show you the mouse data in the next slide. The red bars show you empirical response time distributions for correct choices on the right of each panel, and incorrect choices on the left. So their relative density basically gives you the accuracy, right? The black curves are the model fits to those data. As you can see, that drift diffusion model fits those empirical response time distributions really well. And it can also account for the accuracy. The same holds for mouse data. Okay, this is data that comes from mouse doing brightness discrimination task collected by Ezgi. And here too, we could model those response curves really well with the drift diffusion model. Okay, so it is a useful theoretical tool. All right, so let's come to our common theme: reward rate maximization in this task. In a task where participants have a limited amount of time to make decisions, let's call it the session time, a fixed amount of time, but they could observe the stimulus as long as they want. The pure DDM, the reduced form of the drift diffusion model, prescribes an optimal performance curve that relates error rate on the x-axis here to the mean normalized decision time. So this is an inverse U-shape. This is an optimal performance curve that has an inverse U-shape, and it's asymmetrical. Now, at the extremes, this will make intuitive sense to you. Let's say that your drift rate is very high. Let's say that the stimulus is so strong that there's no way that you are going to hit the wrong threshold. There's no way the diffusion in the evidence accumulation process will result in hitting the wrong threshold. In that case, the optimal strategy is to bring those thresholds as close as possible so that you can make these accurate judgments, because it's an easy task, but a lot of them within that fixed amount of time. All right. The same strategy turns out to be the optimal strategy also for cases in which the task is very difficult to the point that there is no signal in it. Like the first example that I have shown you on the left, right? When there is no signal in that random dot motion discrimination, random dot stimulus, the optimal strategy is again to bring those thresholds as close as possible, because whatever decision you are going to make will be at chance level anyway. So the best strategy is to generate as many decisions as possible. For any error rate in between, you should accumulate some evidence, okay? And that determines, as I said, the mean normalized decision time. Now, Rafael Balci, back in 2006, tested a large group of participants in a single session. And he found that only 30% of participants basically set their decision times that is in line with this optimal performance curve. So 70% of the participants were spending too much time accumulating evidence, right, with respect to that optimal performance curve. Majority of participants basically had accuracy bias. Okay, they just wanted to be accurate to the point that it hurt their reward rate. Okay, so one of the questions is, well, maybe those participants are maximizing another function. Maybe they have the subjective penalty for making errors. I think most of you guys would understand what I mean by that. We are all scientists, right? We try to be as accurate as possible. Or when you are taking a task, a speeded task, you might spend too much time on one question because you might not want to be wrong. Okay, so you can basically introduce that extra parameter Q here, which can code for the relative penalty that, or the subjective penalty that you experience for making errors. And such a function will give you a family of optimal performance curves that I'm showing here. So for instance, if the subjective penalty for making an error is equivalent to the reward that you would get from accurate decisions, your optimal performance curve would be this. And sometimes maybe you experience more penalty for making an error than the reward that you would earn making a correct choice, in which case optimal performance curve look like this, right? Basically, they can go to infinity for low accuracy levels. So it's possible that these participants are basically maximizing a different function, all right? And I did use this this conceptual story in some other research that I did with patients suffering from obsessive compulsive disorder. But today I will argue that there is an alternative. There's another possible reason why most of these participants have this accuracy bias. And I will argue that, in fact, that accuracy bias might be an adaptive bias in response to timing uncertainty. Okay, so that comes. Yeah.
What? Sorry, you have 10 minutes left.
Oh, okay. I'm going much slower than I expected. All right. As always, I'm a bad timer. All right. So in order to maximize the reward rate, what should you do? You should have an estimate of the reward rate. Okay. So what's the reward rate? It's the reciprocal of the time between rewards. So here at the bottom, I will speed up my presentation a little bit. On the bottom, what you see is expected reward rates as a function of normalized thresholds, normalized for different rates. The peak of those reward rate curves are the optimal thresholds for different rates, all right? What I would like you to look at is, to notice, is the asymmetry in the reward rate curves. If you have timing uncertainty, that uncertainty will be inherited by the estimation of the reward rates, because reward rate is a derived quantity and time estimates go into that quantity, right? So if you have a misestimation of the optimal of the reward rate by epsilon, underestimating that optimal threshold will cost you more than overestimating it. Okay, so if you have any uncertainty in your reward rate estimation, it's better to overestimate the optimal threshold than underestimating it, which suggests that there should be a positive relationship between the level of timing uncertainty that you have and how far you are from that optimal performance. Okay, as I said, I had to speed up my presentation because I don't have much time left. That's exactly the relation that we looked at. In fact, we ran multiple regression here. First, we ran it in different ways. First, we want to put in the Q parameter that I have mentioned 2 slides ago as the first predictor, which is not fair, by the way, because that Q is estimated from the deviation from the optimal performance curve anyways. But even after you enter Q parameter, estimated Q value as the first predictor, where the predicted variable is deviation from the optimal performance curve, timing uncertainty can still explain a significant amount of variance in those deviations from the optimal performance curve. When you enter the timing uncertainty first, you can explain 41% of the variance in the deviations from the optimal performance curve. These are the same similar analysis after modeling. So we calculated the optimal threshold for different participants, and here are the normalized deviations from the optimal threshold. And on the x-axis, you see the timing uncertainty measures, coefficient of variation. You see a strong relationship between it. Okay. So the seemingly suboptimal perceptual decisions might also be simply an adaptive bias to accommodate timing uncertainty. Now, my aim was to show you the overlap between timing and decision making at the level of generative processes. But as I told you, Pat Simon presented this model a few weeks ago. And for the sake of time, I'm going to skip that section. All right. Now, I'd like to come to this in the last 7 minutes, I believe, to the discovery that we have made with Başak. And a lot of groups followed up on this already. So the key question for me now at this point in my research is, how is that timing uncertainty integrated into decision optimization? Okay, and we have done some modeling work to see if, without any representation whatsoever, if animals can approximate such a performance, for instance. Most of the time, the qualitative answer is no. Okay, even if they can converge on an optimal strategy, it would take them a very long time, much longer than what we see in the data. And the way that they would approach it doesn't seem like anything we see in the data. One possible answer to this question is maybe subjects can keep track of the direction and magnitude of their errors in their estimates of time, which can be turned into an aggregated form of a representation of timing variability. And this is what I refer to as, this possibility is something that I refer to as metric error modeling. Okay, so the task we ran was very easy. Standard temporal reproduction task, participants are given a target interval, then they're asked to reproduce that interval. We had tested participants with different targets, let's say 1.25 seconds, 1.2 seconds, 2.5 seconds. I don't remember the exact durations, but we had a huge range. I think this paper had 3 or 4 experiments, maybe even more. I mean, we can ask Başak, she ran all those experiments. But then we asked participants this question that they found really odd. We said, do you think you over-reproduced the target interval or under-reproduced it? And then we asked them, that was the second question. That was the first question, sorry. Then we asked them to answer, to give us a confidence rating for their reproduction, time reproduction, all right? Now, participants find this odd because presumably they reproduce in that interval thinking that they did their best, right? They wouldn't have released the button any earlier or later because they think that the target interval has elapsed at that time, so they released the button. Then we asked them, did you think you over reproduced or under reproduced? Do you think your reproduction was shorter than the target or longer than the target? Again, for the simplicity for the sake of time, I'll skip this data, which shows that they can. I'll come to this data, which shows it in a clearer fashion. Here we ask participants to mark on a sliding scale where the reproduction was with respect to the target. And what you see is a very nice positive relationship between timing errors and participants' directional error magnitude judgments. So if participants under-reproduced the interval, they indeed marked it to the left of the target. And how far they marked it to the left of the target was related to the actual magnitude of the errors. The same holds for over-reproductions. So it seems like participants can keep track of both the direction and magnitude of their timing errors, and maybe that results in this aggregate representation of timing variability, which is then used to determine this adaptive bias in temporal decision making and perceptual decision making. We have seen very similar things for numerical estimates, numerical reproductions, spatial reproductions. You do see the same results. So now we use the term metric error modeling to refer to all of these results from different magnitude domains. I believe I don't have time, so I'll conclude my talk here. Time perception and decision making are closely related functions at multiple levels. Many decisions, temporal or perceptual, are adapted to account for uncertainty in the representation of magnitudes. The same processing dynamics of noise evidence integration can account for both decision making and timing. That's the part of my talk that I didn't get to cover. Humans can estimate the direction and magnitude of errors that arise from representational uncertainty, which might mediate the adaptive decision making to incorporate timing/numerical uncertainty. And this is another result that I didn't get to talk about, but metric error modeling appears to be a domain-specific ability. It doesn't seem to be related to metacognitive accuracy in two alternative force choice. So these were basically samples from our research agenda. there's a lot more data there that were collected in my lab and in collaboration with other researchers. These were just sample data to highlight the main points. And we have a lot of people in my lab and collaborators that have contributed to this line of work, which I would like to acknowledge. And obviously, I also would like to acknowledge all the funding agencies that have supported the specific data that I have shown today. So thank you for your attention. I'm sorry that I kind of went over time probably, so I can take any questions that you might have.
Thank you, Fuat. It was really interesting. So yeah, if anyone has any questions, you can raise your Zoom hand or you can put it in the chat and I can ask it for you.
Let's see. How do we raise our
Yes.
hand?
Well, you're already speaking, Randy. You can go ahead and
Hi,
ask.
Randy.
You know.
You know.
Great to see you, Randy.
But that's I'm quelling over the elegance of what you've been doing. But can you say a little more about the domain specificity of the metric error?
Thank you for asking that, Randy. So what we did here is that we tested the same participants in numerical estimation task, temporal reproduction task, and line length reproduction task. So the same participants in random orders took all of these tasks, and they were asked to estimate their estimations, first order test performance, right?
Yeah.
They were asked to estimate if they were underestimating or overestimating. They were asked to provide a confidence rating. And then what we took was we took the slopes that determine that relationship between actual errors and the subjective error ratings, right? Yeah. And all of those slopes seems to be significantly related to each other across all of these domains. But to be able to show if such a metacognitive accuracy also correlated with two alternative forced choice or metacognitive accuracy in the two alternative forced choice task, we calculated the method D prime measure. Basically, we relied on the data that us participants, if they were shorter or longer, or they were overestimating or underestimating in the magnitude domains. And for the two alternative forced choice, we asked them to provide if they were correct or wrong after each choice that they have made. From which you can get a method D prime measure. And when you relate all of those to each other, we see that method D prime measure was associated with each other across all magnitude domains, but not with the method D prime in the two alternative forced choice. That is the data that I rely on to claim that this is a domain specific ability, and it does not generalize to perceptual decision making. That have been said, I have to talk about another data that we collected from participants that have autism. High functioning autistic participants seem to have accurate temporal reproductions, for instance, compared to neurotypically developing participants. But when it comes to their temporal error monitoring, they don't seem to be able to keep track of their errors in their time reproductions. And they don't seem to be able to keep track of their errors in two alternative forced choice either. So despite the fact that I do say that this is a domain specific ability, data that we have gathered from individuals with autism suggests that there might also be a level of overlap between the two. We have designed neuromodulation studies with TMS to be able to see if we can affect these metacognitive performance in both tasks differentially or in an overlap fashion, but we didn't get to run those due to COVID-19. But my simple answer is that we looked at the relationship between the slopes in each of these tasks, and they seem to be significantly related to each other in all cases, as I have demonstrated down here. Randa, I can't hear you.
Okay, I'm just digesting that. So it generalizes across a lot of things. So I'm trying to ask myself, what domain are we talking about?
We are talking about magnitude domains, right? If you take Vincent Walsh or your own take, that time, number, distances might have a common representational basis, I would call that a magnitude domain, and anything else is non-magnitude domain.
Oh, okay. Thank you. Okay. Yeah.
I think Martin has
Yes,
raised his
exactly.
hand.
Yeah, Martin, go ahead, please.
Hi, thank you, Fuat, for this nice talk.
Thank you.
Really nice work. So my question also is related to the magnitude work. So I found it very interesting that you compare different magnitudes with this drift diffusion model. But I always wondered in my own work also if timing, if that does not add a different component. For example, when you compare the dot clouds with 30% of moving dots and timing. So it seems to me that when you have this dot cloud, the signal does not change. So it's always 30%. And you can say, okay, well, I'm not sure. So I wait another 5 seconds until I'm really sure. And during that, the signal itself doesn't change. But this is essentially different for timing, right? So if you have 5 seconds, already waited 5 seconds, then you cannot say, I'm not really sure if 5 seconds have elapsed. So I wait another 3 seconds until I'm sure that this has been 5 seconds. So the signal itself, the magnitude itself changes when you're waiting.
Well,
I wonder what your thoughts are about that.
I do see your point. If you take a generative process level look at the decision process that underlies this two alternative force choice versus timing task, you do see actually that the strength of signal doesn't change during the trial, if that's what you were referring to. So this actually gives me the opportunity to touch on top DBM. So in two alternative force choice, we assumed two thresholds, right? An average drift rate by which you are approaching the correct threshold, and there's the diffusion coefficient that I have mentioned. That's the noise in your evidence accumulation process, and that's why SAT or speed accuracy trade-off comes into play. In timing, you can assume something very similar, but instead of two thresholds, you can assume that there is one absorbing boundary, and you can still have one drift rate that holds that holds its value the same, that stays constant within a trial. In fact, you can introduce variability to it from one trial to the next, but for the sake of simplicity, that's not what you have. And the threshold first crossing time of that decision variable can determine your time estimates or time response. The only difference between the conventional, aside from the fact that now we have a single threshold rather than two thresholds, in terms of the evidence accumulation process, the only difference between your conventional drift diffusion model and this time adaptive Poisson drift diffusion model of interval timing would be in the diffusion coefficient. Okay, in the case of the interval timing model, the diffusion coefficient would scale with the square root of the drift rate, whereas it stays constant in the conventional drift diffusion model. So I don't agree with you in that the decision process or the signal strength changes as a function of time within the trial. In fact, in order to model these temporal error monitoring results, what we did was we combined top DDM, the interval timing model, in a sequential fashion with the conventional DDM. So what we assumed was very simple, actually. We said when you are timing an interval, you are actually using multiple timers. For the sake of simplicity, let's say that we have two timers. One of them is a motor timer that drives our behavior, and one of them is a sensor timer. And let's say that they are coded at different cortices and things like that. So what we assumed was that you run two different timers, one of them determining your time response, and the other one is helping you to keep track of time independent of that motor timer. Once both of your thresholds hit, once both of your decision variables hit the single absorbing boundary, based on which diffusion process hit that threshold first, you can run a second level diffusion process towards a vertical bound that is located at the threshold first crossing time of the slower timer. The direction of the drift rate or the sign of the drift rate will depend on which timer hits the threshold first, motor timer or the sensor timer. And the strength of the absolute value of that drift rate can stay constant. You can make it depend on the distance, whatever. But when that second layer or the second conventional drift diffusion process hits the vertical bound that's located here, that can be used to make a judgment about the degree of your timing error as well as its direction. So in none of these, neither during the timing process nor during the second level drift diffusion process, the signal level changes. If that's what we were referring to. What you are suggesting, though, has an interesting implication. If, let's say that the signal level changes within the trial, that we do not rely on a constant signal to noise ratio, that would open the path to make online corrections to your timing responses. And I find that a very interesting possibility. That is, if our timing responses are indeed subject to online correction mechanisms that might be relying on temporal error monitoring. Okay. Another possibility is this. Instead of having these two timers, we can come up with an explanation that relies on scalar expectancy theory, or the information processing variant of set, which assumes that we are picking a random sample from the memory to make temporal judgments, right? Maybe as soon as your timer hits the threshold, you are picking a random sample from your memory, as set assumes, and the distance between the two can be subject to a second level drift diffusion process, which would give you the same thing. Or since these are tasks that require participants to reproduce an interval again and again, maybe there is some sort of a Bayesian inference that takes place. There's a regression to the mean type of effects in a sequential fashion, and such biases might be dissociated from your object, from the output of your timer, and maybe that's what we rely on to make these temporal error judgments. So I think there's a number of possibilities there, but most of those assume that the signal level doesn't change within a trial. One thing that I would like to emphasize here is that whatever I'm telling here refers to temporal error judgments or numerical error judgments or spatial error judgments on a trial-to-trial basis. Okay. It says nothing about if participants do have a very general idea of their over-reproduction or under-reproduction of time intervals at the end of a session. And your data actually shows that they can't, right? So let's say that we speed up the interval timing process. Let's say that we increase the drift rate here by, let's say, by changing the stimulus property. such a model can still keep track of errors from one trial to the next, but it cannot keep track of this generalized bias in time responses. Okay, so so I think there are a couple of outstanding questions there that can be approached with this decision theoretic framework that we are offering. Okay. So that was a long-winded answer, but any other questions?
So we are out of time, but if you do have a couple more minutes,
I
Elliot.
do, yeah.
Okay.
I'll be more than happy to take more questions.
So yeah, there's one more question.
I think Elliot has raised.
Yeah, exactly.
Yeah.
Please go ahead.
Hi, Fuat. Nice to see you.
Nice to see you too.
Talk I very much enjoyed. I have a kind of a two-part question, but I guess the second question is contingent on the first. Maybe I should know this, but when people are able to identify that they've made an error one way or another, do they accommodate that on the next round? Do they then, if they thought that they just overshot, do they then undershoot on the next one?
We looked at that, and I think Başak might have a better memory than me about this. The first look suggested that there's not a very strong evidence for that. Okay. But as far as I remember, Martin Wiener with one of his students had data that shows that there is these trial-to-trial adjustments.
Okay, so that leads me into the second question, which connects to what Randy was asking about. Is I can imagine that one way you could look at the question of domain specificity versus not is to actually do a crossover. And if there was, I mean, it might not be that there's enough of an adjustment, but if people were adjusting based on errors and it was somehow domain general, you might see that, I mean, you might see it in evidence where if you did a time task interleaved with a numeric task or a spatial task, right? Where you had a time one, right, they overestimate, then you do the spatial one and see if they then underestimate to accommodate. That might be a way of kind of getting at that. The problem is that, you know, that sort of experiment, you know, a null result would be hard to interpret. You know, a result where something actually happens is pretty good evidence that there's actually a domain general mechanism involved.
Elliot, it's great that you say this because we designed that exact study, but after not seeing a very strong evidence for these trial-to-trial adjustments, we set it aside, and we call it spillover effect actually. Okay. If there's any spillover corrective actions between different domains, and if they do break when you interleave an unrelated task, sort of thing, right? Yeah, that's a great suggestion, and that's something that we would like to revisit actually after seeing Martin's data to see how strong of evidence we have for these trial-to-trial adjustments. And of course, and there's data in the literature, in rats even, obviously not asking for these metacognitive ratings, to see if their time responses changes from one trial to the next. Warren Mack had some data that showed that, yeah, there is some adjustment. That's certainly something that we would like to revisit without asking participants to do these metacognitive judgments, though, because when you ask them to say, did they over-reproduce, under-reproduce, that kind of contaminates also the data, right? So I think what we would like to look at, and we can look at it now, is these simple temporary reproduction tasks to see if there are adjustments from one trial to the next. And depending on the strength of the evidence, we can revisit that spillover design that you are also referring to.
Oh, that'd be great. I'd love to see that. I'd one last suggestion before I let everybody go.
Please.
There is, my kids a while ago played a little, it was like an iPad iPhone game, and it was called Stick Hero. And the entire game was to get a stick of a particular length. And it just grew over time the longer you held the button. And it was exactly a spatial temporal estimation task of exactly this flavor, and they played it endlessly. So one, it suggests a task that you might be able to adapt for the lab, and be more interesting to humans. And two, you might actually try and reach out to this company because I'm sure they have tons of data. that you might actually be able to tap into as like a natural data set that, I mean, I don't know how much they record, but I'm sure they have in-house tons of data.
Right. Well, thank you for that. I mean, if there's any consent that participants have, or players in this case, have provided, that would be a great thing to.
Yeah.
So
yeah, it's
look
called
into.
Stick Hero.
Okay, I kept note of it. Thank you.
Okay. Well, good to see you.
But what you said is interesting. So this is actually maybe relevant to a lot of junior scientists in there. So all of these tasks, their downside is they're super boring, right? Especially if you are running these multi-session experiments, you lose a lot of participants sometimes after the first session, second session, because they just don't want to, reproduce a line length, or they don't want to reproduce 3.7 seconds again and again and again. So one way to overcome that is to gamify the tasks, and that's something we have looked into. The DRL schedule we have gamified, and participants seem to enjoy that better. But that's certainly a way to go that I think everybody will want to consider, at least in the kind of work that we do. Yeah, that's a great suggestion. Thank you. I have time if other participants would like to remain and have more questions. I'm more than happy to address them. Otherwise,
I'm not seeing.
I still haven't found. I still haven't found out how to raise my hand. I've been clicking on everything I can click on. Returning to the multiple, I stuck this in the chat thing too, but David Freestone and I in a series of experiments showed that the mice distinguish between external variability in the target itself and their internal variability. And if you think about it, that I don't believe there's any alternative to the conclusion that in fact they're running multiple timers. Because how do you know measurement error? The only way you know measurement error is measuring the same thing more than once, right?
Right.
But as that Greek philosopher pointed out, time is such that you can't step into the same river twice, right? So when it comes to time, the only way you can measure it more than once is to measure exactly the same interval with multiple timers.
That's right. That's right. Indeed. So that's another thing that we have looked into in the DRL task to see if rats, I believe it was rats, or I have to go back to the papers. It was either rats or mice. We did a lot of work on this stuff, so sometimes I get confused. To see if they can also adapt their wait times to maximize reward rate when you introduce this external variable to minimum wait times. They seem to they cannot adapt their responses in an optimal fashion when you introduce this exogenous uncertainty. But again, these things are rather peculiar to the tasks, and maybe we should have tried a different task to see if they can do it. But one interesting question that we are after now is if non-human animals can keep track of their temporal errors, right? We have a design in mind where animals are reproducing an interval, like a minimum wait time on one lever. And the second lever has this response window during which animals can claim the reward. And we are planning to look at the response rate as a proxy for confidence rating, right? Our prediction is that, for instance, if it's a DRL-like schedule where they have to press the lever for a minimum amount of time before claiming a reward to get reward, we are predicting that longer the wait time is on the first lever, higher the reward rate will be on the second lever during this variable response window. We looked at that in the FCN schedule. So those animals that we have, that I've shown you the results for, we ran the exact same study with another set of animals. And at the very end of that experiment, we did introduce this second lever response window. The data didn't look very clean. So I mean, in some mice, it seemed like they could keep track of it, but in some others, majority of the time, there was no relationship. So now I'm thinking on ways to adapt that procedure, maybe to have a cleaner measure of these confidence ratings or whatever proxy that we are going to use for mice, and that would be rather interesting to see. Okay.
Have any other?
That's me again. I don't know if it's allowed, but I want to cross talk with Randy about the point of multiple timers. I'm not sure I understand it entirely. My impression would be if you had a single timer, right? And let's say there was a motor latency, right? So there was a time that you initiated your movement, right, to create your response, but there's a latency that is uncertain, right? That you don't know. So you can still have one timer and then observe an error because you see when your finger hit the button, you get visual feedback, perceptual feedback, experiment feedback, some sort of feedback that can differ from your target, right? And therefore you can adjust your initiation point, which is not quite the same as your timing point, even with a single timer.
I need to make clear the nature of the task that David and I,
Okay.
these were independent things, by the way. He ran his experiment. I with Aaron Heifetz, I ran mine. We didn't know about that. We'd been running the same thing until several years later, but then we put them together in the published report. It was a switch procedure, right? Where
okay, I know.
yeah, okay. And so your explanation, I think, doesn't apply. And what we did was, so in the switch procedure, you have these temporal goalposts, right? So we added wobble to the goalposts. In fact, very extreme wobble, right? So you would expect that the variability in their switch time would go up if they couldn't distinguish, right? But in fact, the variability, if anything, went down. That is, they given a tougher task, they pulled up their socks and they timed their switches even more precisely.
Okay, so that doesn't work.
Yeah,
idea. I was thinking more in terms of Fuat's task.
Right. Yeah, what you are referring to is T naught in DDM, for instance, right? So these non-decision time related delays. Yeah, that's that's something that participants can indeed rely on in the kind of tasks that we run. But you would expect, I think you would expect to have the same amount of performance if you have different targets. So because that's a constant delay, right? There's a constant sensory motor delay.
So that's assumed to be, but maybe not, right?
That's right.
Maybe a chunk of the noise in the error is actually because of error in the non-decision time, right? In the motor execution and perceptual uploading of the right. I mean, that's supposed to include both things on the front end and the back end, the non-decision time. Right. Yeah.
That's something that I mean, that there are ways to distinguish it in the timing research. That's something that we might want to look into as well. Okay, thank you.
I will lower my hand because I know how to do it.
Ashok is going to tell me how to raise my hand.
Yeah, I'll teach you. I'll teach you, Randy. Don't worry. All right. I think that's it for today. Thanks so much, Fuat, for the really interesting talk. And thanks everyone for the discussion and joining us. So as I said, the talk is being recorded. It will be up on the TRF website and the YouTube channel soon. And then our next virtual club, journal club, will be on December 15th by Nicola Mirek and Nir Ophir. We'll be sending out the announcement and the registration link very soon. Thank you all for joining us again, and see you all soon. Thanks, Fuat.
Thank you. Thanks for having me, and thanks everyone for your attention and questions. Bye-bye.
Bye.